In the past 2 months, you may have heard of a material known as LK-99 creating some headlines in the scientific community. Well, with this giant Twitter storm, or should we say, X storm, thanks Elon for that one, LK-99 caught the eyes of many researchers due to the material reportedly being a superconductor at room temperature. I don't know about you guys, but I was personally ready to enter a world where levitating trains were the norm. But unfortunately, LK-99 failed to deliver on its promise. So what is LK-99, and what went wrong with it? We begin our journey with a description of what normal conductors are. Conductors are essentially materials that allow either heat or electricity to pass through them, ranging from obvious ones like alloys and metals to more diverse and unexpected ones such as the earth, animals, and the human body. Now, I definitely won't advise you to conduct experiments on your pet hamster at home. Resistivity is a property that describes the material's ability to resist the flow of electrons, where this resistance leads to energy loss in the form of heat. Additionally, conductance has a direct correlation to resistivity, which is due to the fact that resistivity gives us not only qualitative, but also quantitative ways of measuring the flow of electrons. This is all nice and dandy, but what exactly gives the conductor the prestigious title of super? Obviously, it ain't shooting electricity like Senator Palpatine. The term superconductor essentially implies that under characteristic temperature, the material displays zero resistivity. There are two important terms that we would like you to know while dealing with superconductors. These are critical temperature and critical field, which explain that there are specific temperatures and fields under which the material acts like a superconductor. It is widely regarded that the pioneer of superconductance is Heike Onnes, who was one day conducting research in a cryogenic lab and stumbled upon this phenomenon in 1911. Yeah, the only thing I stumbled on is the ice cream in my freezer. So we mentioned that superconductors function under specific conditions, right? They need to be at a certain temperature and pressure to exhibit their superconductivity. This is the current issue with superconductors, as they require either extremely high or low temperatures in order to function, making them difficult to use in everyday applications. But what if we could have a material which exhibits superconductivity at room temperature and ambient pressure? Well, that is exactly what LK-99 was supposed to deliver. It was supposed to be a material that can exhibit the phenomenon of superconductivity in everyday conditions, meaning that my dream of levitating trains and much more could come true. The initial paper that started this X-storm was published by researchers from the University of Korea titled "The First Room Temperature Ambient Pressure Superconductor." Here they state that they confirm LK-99 superconductivity through its critical temperature, zero resistivity, critical current, critical magnetic field, and the Meissner effect, where each parameter satisfied the global standards for superconductivity. In other words, the team did rigorous testing on LK-99 in order to confirm whether or not its properties are coherent with those described for superconductors, and according to them, they are. Additionally, they also described the synthetic protocol for making LK-99, which is actually quite straightforward and simple. Essentially, equal molar parts of lanarkite or Pb2SO4 with copper 3 phosphate Cu3P are mixed, placed under vacuum and reacted at a temperature of 925 degrees Celsius. Other than the high reaction temperatures, which are energy intensive, this procedure is rather rudimentary, meaning it could have easily been applied to an industrial setting. We've arrived at a pivotal moment in our exploration of LK-99, addressing the question, why did it fail? This is where we dissect the complexities that led to the unraveling of what could have been a scientific breakthrough. So why did LK-99 fail to be the groundbreaking room temperature superconductor that it was initially hyped up to be? Well, the devil is in the details, or in this case, the impurities. First up, copper 1 sulfide, or Cu2S. This impurity was reported both by the Korean team that synthesized LK-99 and many other institutions. It was responsible for the sharp drops in electrical resistivity that were initially mistaken for superconducting behavior. A copper sulfide specialist named Jane at the University of Illinois stated that copper 1 sulfide undergoes a phase transition at 104 degrees where its resistivity drops dramatically, producing a signal quite identical to the one published in the original LK-99 study. On the left is the digitized graph that Jane made from the paper by Lee, Kim, and colleagues, whereas on the right is a graph from a study done by Hirahara. Quite similar indeed. In order to observe the effects of this impurity, a team at the Max Planck Institute for Solid-State Research in Stuttgart performed synthesis of pure LK-99 via floating zone crystal growth. This is a method that allows the researchers to avoid sulfur, and in other words, eliminate Cu2S impurities. This resulted in a clear purple crystal as shown on screen. When testing the material, the researchers put one nail in the coffin for LK-99, finding that it is not a superconductor but an insulator, as they found that its resistance was in the millions of ohms, way too high for it to be a superconductor. Next, let's talk about ferromagnetism. The half levitation that was observed wasn't due to superconductivity but was actually a result of ferromagnetism. This was confirmed by multiple research teams. In simple terms, ferromagnetism is a magnetic phenomenon where certain materials like iron and nickel become magnetized in the presence of an external magnetic field due to electrons in the material aligning their magnetic moments. Unlike superconductivity, which expels magnetic fields, ferromagnetic materials actually align their internal magnetic domains, amplifying the external field. This is why you see effects like half levitation. It's not superconductivity, but rather the material acting like a magnet. In summary, LK-99's failure as a superconductor can be attributed to impurities, misunderstood magnetic properties, and its inherent insulating nature. It truly does serve as a compelling case study in the rigorous, often unforgiving process of scientific validation. Let's talk about a really cool application LK-99 could have had. Whilst levitating trains that use superconductors do exist, they're still not available to the public, and a major challenge remains, one of them being that the superconducting material needs to be cooled, making the project less financially sound. Currently, the Central Japan Railway Company is working on an SC maglev train, which is set to release sometime this decade. If you're interested in learning more about this topic, you should check out Tom Scott's video where he rode the fastest train in the world. Link in description. So what would LK-99 have meant for levitating trains? Well, whilst I'm no expert on the topic or engineering of levitating trains, LK-99 could have made the program easier. Without the need for cooling or heating the superconductor, some technical challenges could be overcome, and even more importantly, costs can be saved. Furthermore, if you are a chemist, LK-99 could have had some important applications in NMR, or nuclear magnetic resonance. You see, in NMR we are studying the nuclei of atoms where we use superconductors to generate a magnetic field that nuclei can interact with. Subsequently, when we pulse radio waves, the energy is absorbed by the nuclei as they go to higher spin states, and in turn, we get a signal. By using a room temperature superconductor, NMR can be run more cost effectively and additionally more safely, as it eliminates the risk of cryogenic failures. So whilst the authors of the LK-99 paper state that their new developments will be a brand new historical event that opens a new era for humankind, room temperature superconductors are going to have to wait another day. We're now at the end of this video, and we would love to hear your thoughts about LK-99. Do you think if it was a true room temperature superconductor, it could revolutionize our world? Let us know in the comments down below. Thank you very much for watching and supporting our channel. Be sure to give us a like and subscribe if you enjoyed this video, and share it with your friends and family. We will see you guys in our next video. Bye bye.